Okay, great. Awesome. Okay, well, thanks everyone for coming to this lecture, and thanks for the opportunity to give this talk. So what I'd like to do is I'd like to tell you a little bit about some of the advances and some of the new challenges, particularly in the space of deep learning. So in terms of the impact, you've probably seen the impact in the space of speech recognition, vision, recommending engines, language understanding, even in places like drug discovery and medical image analysis. We do see some impact there as well. And what is it that we want to do? Well, ultimately, what I want to do is I want to be able to develop computer algorithms, models that can see and recognize objects around us, that can understand human speech, that can reason and understand natural language, that can move around, explore, plan, and in general display human-like intelligence, right? And in terms of some of the challenges, what are some of the key challenges in the space of deep learning and what we're working on? Well, a big challenge is reasoning. How can we get systems to reason? Attention and memory, I'll show you some examples of that. Natural language understanding is another big area of research, in which is probably going to be most of my talk is going to be focused around reasoning and natural language understanding. Deep reinforcement learning, I'll show you some examples of reinforcement learning research, as well as the space of multi-modal, semi-supervised, and unsupervised learning. So let me give you some ideas of behind learning with natural language. Suppose I give you, this context. This is one of the CNN news articles, and let's say it says, arrested Illinois Governor Rod Blagojevich and his chief on staff, John Harris, on corruption charges and so forth. So it's a little article about, if you remember back in 2008, there was this scandal where Rod Blagojevich, the senator from Illinois, was trying to sell Obama's Senate seat and such. And imagine that I give you this article and then I give you a query, right? And the query says, President-elect Barack Obama on Tuesday said he was not aware of alleged corruption by X. And the question is, who is X? Well, X could be Rod Blagojevich, it could be John Harris, it could be Barack Obama, right? And the right answer is Rod Blagojevich. And so if you look at this particular question, the system needs to understand something about query, right? It needs to understand what's going on in the context in order to be able to answer this particular question. These are quite challenging natural language understanding tasks, right? Because the system needs to understand what is it in the context and the query as well. And so much of the research, processing sequential data has been kind of focused around recurrent networks. And the idea here is you have some hidden state representation at t-1. You have some observation, some input at time t. You combine them, you pass them through some nonlinearity, and that gives you the update for the next time step. And there are tons of different extensions, LSTMs, GRUs, and so forth. And more recently, which is something that I'm going to focus in this talk, is this transformer type of architectures that use a so-called self-attention. But if we look at these systems, right, how do they look like? Well, we can use RNNs, so we can use transformers, to encode the query, right? So there's some way of encoding each word in the query and each word in the document. So that's displayed here. And then, for example, we can use element-wise multiplication to sort of gate interactions between query and document. So it essentially says that, when X visited Prague, Obama met Prague. And so we're basically trying to connect these words in the query to the words in the document, right? And if you kind of look at these systems, you have some form of recurrent network on the query, some form of recurrent network on the text. You have this gating mechanism. And if you look at these architectures are now becoming quite complex. There's a sequential processing at each layer, and you have to have multiple layers in order to produce the answer, right? So you're probably familiar with convolutional neural networks. So you can think of these models as kind of, much more complex. And if you look at the latest research, a lot of it is done in terms of designing what these blocks are, how they interact, and so forth. And we'll see some examples of that in this talk as well. What's interesting about these models also is that they tend to learn some form of attention mechanism. So for example, in the first layer, alleged corruption basically, correlates highly with Rod Blagojevich. And then the second layer, basically Senate seat correlates with, Governor Blagojevich. So it sort of figures out what are the right features in the text that you have to pick up such that you can produce the right answer, right? So you can think of it as learning what the right representations should be. So here it basically tries picking up on these correct, parts of text and, correct parts of sentences so that you can answer a particular task, right? So in this talk, what I'd like to do is I'd like to talk about a couple of projects, very recent project that just, appeared just this year. One of them is in Transformer Excel. These are models that kind of allow you to model long-term dependencies between words and sentences, as well as XLNet, which is a generalized autoregressive model for basically for language understanding. And I'll give you some highlights behind both of these works and how you can use them for understanding language. So how does language modeling works? Well, in some sense, it's part of what's called the density estimation by autoregression, or some way of trying to deal with time series data. So suppose we have a sequence of length t, right? And in this case, density estimation would basically look like this. If we look at the distribution over all the tokens, or all the sequences in our all this sequence of length t, then we can say, well, this probability is going to be given by this conditional probabilities, right? Any join, I can always factorize into the conditionals. And then what I'm going to do is I'm going to pass them through some function g such that I can have some compact approximation of this conditional probability. And this particular function g could be, could be neural network, could be deep neural network. And so the idea here is the following. There is some H1, some hidden state based on some features that gives me probability of x1. Then given x1, you pass it through some function g, right, and the hidden state from the previous time step, and then you get H2. So this one models the conditional probability of x2 given x1, right? And then again, you pass this hidden state forward, you observe x2, so you observe x3, and it goes through this processing, and then it basically looks at the conditional probability of x3 given x2 and x1 and so forth, right? So here you get observations, here you have the hidden states that get updated, and each one of them is modeling this conditional probability. So there's a lot of work done in that space, for example, neural autoregressive density estimation, pixel CNNs and pixel RNNs and so forth. If we're looking at the language modeling, then we can basically think of the problem as the following. Suppose I give you corpus of T sequential tokens or words, right? And then what I'm going to do is I'm going to model the distribution over those words as product of conditionals. And in particular, I'm going to be passing the context through some function f, right? And then I'm going to be passing this conditional probability is just going to be given by the softmax distribution, which is suitable for modeling, word tokens, so discrete data. So here we're basically observing one word at a time, and these are discrete outputs. So this is typically done through the softmax function. But what's more important here is that, how we're going to be looking at the particular function f. What is the choice for the function f, and how can we model these long-term dependencies? Before doing that, let me actually give you one example just to motivate what we're trying to do. So suppose here, we have some context, and this context comes from Wikipedia articles. And this context talks about Napoleon, right? It says in a series of conflicts, it talks about Napoleon and so forth. And then it says, under the leadership of Napoleon, French power rose quickly as the Grand Army conquered most of Europe and collapsed rapidly. And then that's the reference, that's the ground truth, right? It says, after disastrous invasions of Russia in 1812, Napoleon's empire ultimately suffered complete military defeat and so forth, right? So and then it talks about, what happened and, what battles Napoleon fought and so forth, right? So this is the reference. Well, if you're using these language models, what you can do is you can, generate the following. So here we're basically saying, under the leadership of Napoleon, French power rose quickly and then collapsed rapidly after. And this is what the model would generate, just a sample, a Monte Carlo sample from the model after the French conquest of Italy. The victory marked the beginning of the second coalition. Napoleon's rapid advance caused Austria, Russia, Britain, and Russia to make peace negotiations. The Russian army under Prince Mikhail Mikhailovich Shafé, and you can't get more Russian than Mikhail Mikhailovich, commander of the Imperial Russian Army in Switzerland, was able to drive the Austrians off the battle and so forth, right? So it goes on, and it talks about, you know, the French military situation worsened as Napoleon faced several threats related to newly formed army in Europe, particularly Russia itself, which was now on the verge of collapse and so forth, right? And then, you know, the next one, you know, and this is just the generating. This is the model generating one word at a time. And then what's interesting, it also has some notion of long context. So then it says in July 1805, the French First Army entered southern Italy under the command and so forth. And then it says by 17th September, the army marched from Belluno towards Krems. By 29 September, they reached Belluno and conducted an advance against the small Austrian force. By 31st September, the force and so forth, right? So what you're seeing is that the model basically is able to pick up on the dates and have some form of chronological continuation, right? What's interesting here is that this is just an autoregressive model, and the way that these words are generated is basically you just go and you look, you know, you sample from this conditional probability. So given some context, you sample the next word, and then the next word, and then you sample the next 1,000 words, so 10,000 words, right? And what you can see is that there is a consistency because it starts talking about conquest of Italy and so forth. And then, you know, the next paragraph, it talks about how it, you know, entered the southern Italy and what happened and so forth, right? So this is one of, you know, the difficult tasks here is to maintain this long-term dependency context, right? So this is something that, you know, a few years ago, you would have asked me, is this possible to do something like that? I would probably say no, because we didn't have mechanisms of maintaining this long-term dependency as we're generating the text. One of the key backbones of this model is a transformer type of architectures. I won't have time to go into details what the transformer models are, but I'll give you an intuition behind how it works. So typically in the standard language modeling tasks, you know, what you typically do is you say, well, I have a long sequence. What I'm going to do is I'm going to break it into subsequences, right? So this is the first segment, this is the teeth segment, and so forth. So typically, because it's very hard to model these long-term dependencies, you're just breaking it into chunks. And then the idea is that you're going to be modeling each segment independently. And this is what we call with limited memory, because it's very hard for you to take, you know, all these long sequences into account. So typically, you're basically saying this conditional probability of one segment given the previous segment is just the product of individual segments, right? There's independence assumptions. I'm modeling, you know, sequences of length maybe 500 separately. And then within each sequence, you're modeling this, you're doing this language modeling, right? And now in this kind of, you know, kind of architecture, given x1, you predict the conditional probability of x2, given x1. Given x2, you predict the conditional probability of x3 given x1, x2, and then based on sampled x3, given x3, you predict conditional probability of x4 and so forth, right? And so when you train these models, you're training them sequentially, one at a time. And so there is no information flow between these segments. And that creates a bottleneck because if I talk about in this segment, you know, Napoleon entering Italy, then there's nothing here that basically maintains this information, right? Because I'm basically modeling this piece separately. So instead, and then during evaluation, you basically, what you're doing, you're kind of scanning through the sequences of length t, right? However, you know, whatever your computational bottleneck, you know, however much computation you can handle, and then you're basically modeling these conditional probabilities, right? And so you're recomputing everything from scratch. And so the key idea of transformer XL architectures is that to use and cache previously computed hidden states, right? And this is very similar to truncated belief propagation through time or backpropagation through time for recurrent neural networks. What you're basically doing is you're maintaining the states of the hidden variables through time. And you have the segment level recurrence, right? And so you keep the temporal information coherent. Intuitively, what it looks like, let's say we're processing this segment, right? And then at the next time, what we do is we take the segment and we call it a fixed memory segment. So there's no gradient propagation through this segment just because of computational constraints. And then in the current segment, right, whenever we, for example, producing this conditional probability of, you know, x6 given the context, we're actually paying attention to these hidden states, right? And so what it allows us to do is that we save in computation because we can only backpropagate through this segment, right? So all the parameters are being updated in this segment, and this is fixed. So you can save on computation. So as you're processing this information forward, you're maintaining this fixed memory. And that's precisely what allows you to model these long-term dependencies, right? Because this context spans linearly with respect to both the segment length, whatever your segment length is, and the number of layers. So it spans linearly, it basically linearly with a number of layers as well. Typically, for some of our experiments, we've used 16 layers. So we can actually reach out, to fairly long context. So context over here can basically impact the conditional probability over here, right? And so here we also don't need to recompute anything. At the test time, we're just forwarding everything, and the computation basically flows in the forward pass. And so in terms of, mathematics a little bit, what we're effectively using is we're using transformer-like architecture. So H here is basically the nth layer hidden state, right, produced by sequence tau. M here is the memory that's cached before, and SG here stands for stop gradient. So we don't backpropagate through that representation, right? Otherwise, computationally would be infeasible. And so now what effectively what we're effectively doing is we have model parameters. Think of them as just parameters of your architecture. And we basically have what's called query keys and values for transformer type of layer, transformer type of architecture. And what's important is that these hidden states here maintain this extended context. So they can propagate information that we've seen way in the past into the transformer layer. And so when we train this model, this is just an example on training across different data sets. This is in terms of measuring perplexities and such. And here, this particular model achieves state-of-the-art on 5 different publicly available data sets. Which is, and so if we actually look at the attention, what it's doing, here's an example of one of the attention mechanisms. And what you're seeing is that there is a lot of attention that's being paid to the short context. What that means is that basically, the previous 10 words really have a lot of influence on what the 11th prediction for the 11th word should be, right? So short context is really important for generating the next word in a sentence, right? But there are some other settings. Here's, for example, a setting where actually there's attention weights that actually looks at the overall context, right? So it's actually, maintains information throughout, in this case, it was like 640 tokens. Here's another interesting learned attention. It basically pays attention to specific words. And when we look closely at what these words are, most of them actually correspond to dates or some kind of events that happened in the past. So this is interesting because it basically says, I'm going to be paying attention to specific words or specific dates so that, I can generate coherent text going forward. So it effectively learns short context, it learns long context, it learns where to pay attention and such, which is pretty cool. And I think that, here's another example of, just to sort of show you, is another example of a particular baseball player, Keyshaw, which is, he was awarded National League Player and so forth. And, midway through June, Keyshaw has amassed 32 career victories. And this is what the reference is. This is the ground truth. And this is what the model generates, right? And so the model kind of talks about, the Dodgers signed Keyshaw for 1-year deal in July with play option. The deal worth just under $300,000. So it has some idea of how much, baseball players are being paid and so forth. And it talks about, what happened, right? And it's actually pretty good in terms of describing what's actually happened compared to the ground truth. What's also interesting is that, like if I look at, if I look at, towards the very end, it says the following. On May, Keyshaw sustained another back injury. Did not start in August. He appeared in 22 stars, finishing with strikeout and so forth, right? What's interesting here is that the model basically, learned that a lot of baseball players typically sustain back injury. And so here it just basically generates on a particular date, Keyshaw sustained a back injury, even though, he didn't. And so it kind of coherently, talks about what happened in his career and so forth, right? So it learns these long-term dependencies, and it learns the right kind of correlation structure, right? And it's a single model trained on lots and lots of Wikipedia articles. And I think that more recently, there's been a recent paper coming out of DeepMind that showed that Transformer XL with specific architectural changes can be used for stable learning of reinforcement learning, deep reinforcement learning agents, specifically with memory mechanisms, which is very difficult to train. Right? Now, let me, we've talked about language model. Let me quickly talk about language understanding. So how can we actually get some representation from language that can be used for lots of different tasks? So XLNet is one of the state-of-the-art pre-trained models for language understanding. It's in English. So if you're interested, for example, in classification, regression, question answering tasks, document ranking, you can use XLNet. Basically, any task that basically looks at text and maps it to some form of labels or some form of structure, right? And you can look on the website, you can basically collect the data, fine-tune it on the data set, and there's more instructions on how to do that. So question answering, factual question answering, document ranking, document retrieval, document classification, sentiment analysis, all of these tasks could be done with XLNet. So let's look at what this model is. The key idea behind a lot of recent developments and lots of recent advances in language understanding come from pre-training the model and pre-training a model on unlabeled data sets. So the idea is that you basically pre-train the model on a large corpus of unlabeled data, and then you fine-tune it for a specific task, like question answering task, for example. So you've probably heard about Word2Vec, GLAF, and so forth, GPT-2, BERT. There's all these extensions or sort of variants of unsupervised learning. Now, when we think about pre-training objectives, right, and we can have access to lots and lots of unlabeled data, lots and lots of unlabeled text. So when we think about objectives, there are two objectives for pre-training. There is one, which is language modeling, what we've talked about just right now. The idea here is that, you're trying to model the conditional probability of a token given its context. So for example, you say new and then predict York, and then given New York, you predict is, and then you say New York is, you predict New York is and you predict city, right? And so forth. And then you predict the end of sentence. So that would typically what a non-directional kind of transformer like language modeling architecture would do. The problem is that it's forward. It can't take bidirectional context into account. So if I want to get the representation of this sentence, I want to be able to sort of like go forward and backward. The second type of model is what's based on denoising autoencoders, and this is BERT-like model that is also kind of the state-of-the-art for language pre-training. And so the idea here is that what you want to do is you want to mask some words, like for example, you mask the word New York, and then based is a city, you predict the masked words, right? So you randomly mask few words, maybe 15% of your sentence, and then you predict those words. Right, and so now based on just this context, you're predicting these words. The problem with this approach with denoising autoencoders is that these predicting tokens are independent of each other. So given this context, you're predicting new, and then given this context, you're predicting York. Right, so it's not ideal. So what we've been looking at permutation language modeling, permutation variant language modeling. The idea here is the following: you sample a factorization order, and then you determine sort of attention mass based on that particular order, and then you optimize the standard language objective function. So depending on the order, you optimize the language modeling. This is autoregressive model, and then here you're averaging over all possible factorization orders. And the idea is basically the following: if I'm trying to model probability of A and B, I can either model as probability of A, probability of B given A, or I can model as probability of B, probability of A given B. That's basically the key idea. And so here, for example, if I tell you, let's say I have a sentence, New York is a city, and I tell you, here's the factorization order, New York is a city. Well, if I look at the probability of New York as a city, given this factorization order, I can say, well, it's probability new, and it's probability York given new, it's probability is given New York, and so forth. On the other hand, I can give you a different factorization order. I can say city A is New York. So if I'm trying to model this particular joint probability, I can basically say, well, I'm first going to model probability as a city. Probability is A is a city. Probability is city A. Probability of New and probability of York, right? Notice that the sequence itself is not shuffled. It's just how I factorize that sequence depends on the ordering, right? And then when you look at the attention marks, what is it that you condition on the context? That determines by the order, right? So for example, if I have the order 3, 2, 4, 1, and I'm trying to model conditional probability of 3, then I'm just conditioning on some memory, right, or whatever came before 3. If I'm trying to predict, in this case, 3, but 2 and 4 happened before, then condition on 2 and 4, I'm modeling 3, right? Or in this case, if 3 comes the last, then I actually take 1, 4, and 2, 1, 4, and 2, and that's being used to predict X3, right? So you can basically see it kind of looks at all possible orderings to predict a particular token 3. So it sort of takes this bidirectional context into account by summing over all possible factorization orders, right? Which is, again, just modeling the joint distribution of these tokens. So that's the idea. So if you look like a BERT-like objective or denoising autoencoder type of objective, then you're basically saying probability of New and probability of York are independent. On the other hand, if you have an XLNet type of objective, you can say probability of New is a city, probability of York given New York. Or if you have a different factorization, you can model these conditionals. And so effectively, you're modeling dependencies between New and York. You also have bidirectional context because factorizing over all possible orders gives you this context. And so here you're just using, you factorize the joint probability just using the product rule, right? And this product rule holds universally. This is how you can decompose any joint distribution. So that's the idea. Now, one particular thing to emphasize here is that if you look at the standard parameterization, right? If you kind of look at trying to do that, then it turns out that if H, your hidden state, doesn't contain the position of the target, the word that you're trying to predict, then essentially it reduces to the bag of words, right? For example, New York, is it X3 happens in position 3, or is happens in position 4, or is happens in position 5? If you don't give that information, then you're basically becoming bag of words. So we have to sort of find the solution. And the solution here is when you're trying to predict a particular word, you also predict it at position ZT. So you're basically saying at position 5, what is the word, what's the word should be, right? Or at position 10, what the word should be, given the context, right? So it cannot cheat by just doing bag of words. It actually has to predict the particular word at the particular position. And so, for example, suppose you have factorization order 3, 2, 4, 1. Then if you're trying to predict 2, you depend on X3 and X4, right? And then, if you try to predict 4, then it depends on X2 and X3, right? So here it just depends on X3, here it depends on X2 and X3 to predict 4, right? And so here G, you can think of G as basically telling you which position you should be predicting. Is it position 2 or position 4, right? The important thing here is that when we're building these models, we cannot see ourselves, right? So for example, from 3, we're trying to predict 2. Because if there was a self, you cannot see yourself, because if you see yourself, then the problem becomes trivial, right? So, but it turns out it also creates slight problem for us. The reason why is because this representation should not include X2. And this representation should encode X2. So here it shouldn't, and here it should, right? Because when we're trying to predict 4, we want to rely on 3 and 2. So that basically, it requires us to do one more trick. And the idea here is whenever you look at X4, when I try to predict X4, you actually want to have access to X2 and X3, right, in the first layer. So basically, we design what's called a two-stream attention. And, you can think of the two-stream attention. There is a content stream, which basically looks at the entire content and just propagates it forward. And then there's a query stream. And the query stream is essentially saying, well, given the context, what should I predict at a particular location? So you can think of a query stream as like a decoder. Given the context, predict the next word. And the content stream as an encoder. Given the whole context, how do we encode it, right? And so here, we basically have these two-stream architectures. The idea here is that the query stream uses the position but cannot see the token itself. It's trying to predict a token. And the content stream basically uses both. What is it trying to predict as well as where it's trying to predict it, right? And so, only H is going to be used during fine tuning. So only content stream is going to be used for fine tuning, and the G is basically used for optimization, right? So we can think of content stream again as a similar to encoder, and query stream is a similar to decoder. Encoder just encodes the representation of the sentence. Query stream basically tries to predict the word at a particular location. So we can adapt XLNet architecture for sequence to sequence, for text generation, and so forth, right? And so again, just to kind of like summarize, we've looked at the independent assumptions of denoising autoencoder BERT-like models. We can model this permutation invariant language modeling. Standard, if you just use standard parameterization, we basically have bag of words, and we have this representation with positions, and then trying to predict self and others, we're basically using two-stream architectures to kind of make this reparameterization work for us, right? So these are kind of, key highlights behind XLNet, the architecture for XLNet. And so when we've tested the XLNet on 20 different tasks, we basically were able to achieve state-of-the-art results on 18 tasks. So for example, if you look at tasks like race, which is a question answer, squad, which is, a standard question answering data set, which is quite difficult actually. We basically outperform on a number of tasks. So if you look at all of these data sets are language understanding data sets. Some of them are question answering, some of them are classification, retrieval, sentiment analysis, reasoning, multi-hop question answering, and so forth, right? And so what we're seeing here is that a couple of things I want to highlight is that this one was trained on about 40 gigabytes of data. This was trained on just Wikibooks, so Wikipedia and books data set. So it's it's about an order of like 5 to 8 gigabytes, I believe. And this is what the BERT representation is. So what's interesting, one interesting thing to observe is that as you increase the size of the data, for some of these data sets, performance improves. So as you increase the pre-training data, right, like basically going to 40 gigabytes of data. But sometimes actually performance, it hurts the performance. So from smaller data set to larger data set, it actually goes down. So sometimes the quality of unlabeled data set also matters, right? And so here, basically, we're seeing that the gains of using 10 times as much data are smaller than switching from BERT to XLNet. So for example, what that means is that finding the right loss functions for pre-training actually matters a lot, right? So here's just some examples, basically saying that Transform XL improves performance on long sequence tasks. So for example, here, for these types of tasks like race and squad 2, having a transformer architecture actually gives you big boost in performance. So because it can model these long-term dependencies, right? And then permutation language modeling improves the performance. So if we look at denoising autoencoder BERT-like models versus permutation invariant architecture, then again, the numbers get improved, and then there's a lot of different few tricks to kind of like get it right. Right, but it's quite interesting because in a lot of these data sets, the performance is actually pretty good for these, fairly complex tasks, sentiment question answering tasks. Okay, so well, one of the key things I want to highlight is that language modeling itself is basically a density estimation problem, right? And it's a very rapidly developing field, sequential modeling, autoregressive modeling. And if you think about, just the architecture of XLNet, the architecture itself, pre-training is just basically a language modeling problem, right? We choose the factorization order, and then we solve a language model. We update the parameters using language modeling task. And basically, you can also model long-term dependencies with Transform XL type of architecture, right? Maintaining this long history. And the reason why I want to highlight that it's a language modeling task is because, it's an interesting topic of research. And sometimes I think that the original paper for Transform XL was rejected from one of the conferences, and people said, well, who cares about language modeling? Show us results on some real tasks. And this is just to highlight that if you have a stronger or better language modeling model, then I think you should be able to substantially improve over a lot of downstream tasks like machine translation, question answering, and so forth. Okay. So now in the last sort of 10, 15 minutes, let me kind of show you also some connections to reinforcement learning. and with memory, and then I'll show you some connections with natural language understanding and reinforcement learning. So what is reinforcement learning? Well, reinforcement learning is all about learning behaviors. What you're effectively doing is you're learning to map sequences of observations to actions to achieve a particular goal, right? And the idea here is that you have an agent, the agent takes an action, turn left, turn right, go forward, or other types of actions. You get the new observation or the new state, and sometimes you get the reward. And the reward is basically telling you whether certain actions were good or bad, or you've achieved a particular goal state, and that was a good behavior, right? And if you look at, the space of deep reinforcement learning, then you're effectively replacing the agent with, basically a neural network. So here you're learning the policy that goes from observations, think of it as high dimensional observation, to some actions, right? And in the last sort of, few years has been interesting work on learning external memory. And I think it's a fascinating work where you're basically learning these differentiable read and write operations into the external memory. So you can remember something about the past so that you can act optimally in the future. So, one of the things that we've been also interested in looking at is learning the structured memory, external structured memory. Let me give you an example of why this is a difficult task. And this also connects to this notion of learning long-term or having long-term dependencies. So suppose you are in some environment, this is a maze environment, and suppose that you have some indicator, and if the indicator is blue, then you have to find cyan block. If the indicator is green, you have to find red block. So you can think of it as like the procedure which basically tells you that depending on what indicator it is, you have to find a different target. And the time that you spend from finding out where the correct target is could be quite long. So you need some notion of memory to remember what you've seen in the past. So again, so you can take optimal actions in the future. This is very difficult to do with traditional systems like, recurrent networks and LSTM type of architectures, because maintaining this hidden state over time becomes a challenging task. So here we've been looking at the neural map architecture, which has a very specific inductive bias, right? Which is we structure memory into W by W grid of k-dimensional cells. And for every position that we are in a maze, we basically write to the corresponding cell in the memory. So for example, if the agent is here, you're writing over here. If the agent is here, you're writing it over here, right? So the idea is that as the agent explores the environment, you're learning what that memory is. So you can store, the right information in your memory. So it kind of looks as follows. Let's say you have some observation, you get some features from your observation, you write it in the memory, you take an action. At the next time step, you read something from the memory with attention, basically figuring out, can we extract some information from the memory? We update the memory, we take an action, and so forth. So if you look at this architecture, it almost looks like, a recurrent network, but you have this specific memory block, which you're updating and you're maintaining as you go through time. So here you can learn to store important information. So here, for example, you can learn to store the indicator variable, or you can learn to store anything about the environment that's useful for you to solve the task. And notice that, if I gave you the indicators beforehand, then the problem would be trivial, right? If I told you beforehand, well, if you see blue indicator, find the green target, then the problem becomes trivial. The question is, how do you discover it on your own, right? Through the reinforcement learning. And again, the idea here is that the agent would basically enter the scene, move around, find some target, get positive reward, and you say, okay, that's a good target to go to. Next time you go to this target, you get negative reward. And at that point, you start figuring out, okay, sometimes you get positive, sometimes you get negative. And through the process of learning, you start figuring out, there is this indicator that actually controlling where should I go, right? Basically some basic notion of causality to some extent, right? And so here's an example where the agent basically, in a completely random maze, a new maze, moves around, finds the wrong target, backtracks, so it reads from the memory that it reached the wrong target, goes around, explores the environment, and as it's exploring the environment, it basically, goes around in this maze up until it finds, the right target. And as it finds the right target, it goes to the right target, right? So that's why and the memory mechanism specifically learned to store parts of the mazes, but also it learns to store the indicator as well. right? We also looked at the task of, another interesting task is the task-oriented language grounding. So here, imagine I give you instructions. Go to the short red pillar, go to the largest object, and so forth. And you want to be able to do well on new instructions that you haven't seen at the training time, right? So here's an example of an agent that basically navigates around and learns the meaning of different words. So for example, what is red pillar? What is short pillar? So things like, tall object, things like tall is very difficult to describe, right? Because tall is a relative concept depending on which objects you see in the environment. And so through the process of learning, it basically learns, go to the tall red object, or go to the blue object, or go to the smallest object in the scene, and so forth, right? So it's a problem of language ground. Go to the smallest blue object, right? So it figures out what does the smallest mean. And so through the process of learning, it basically starts understanding what these instructions are and what is the meaning of, words like tall, small, green, torch, and so forth, right? So it's a little tiny step towards, grounding what is it that you're seeing versus what the meaning of, the meaning of words. And if you look at kind of architectures, again, as I mentioned before, these architectures become more and more elaborate. Okay, can you hear me? Okay, great. For some reason, the system just muted me. Okay, so here you basically have these architectures that are now more complex. You have an image, you have a query that goes through, a fairly complex architecture where you're basically trying to associate words with specific objects that you see. So these are, special attention and dual attention and so forth, right? To solve these, these more complex tasks. The other thing that I wanted to show you is this notion of exploration. So here's an example of an agent navigating an environment. This is what's called metaphor environment. These are real houses that are kind of scanned, and the agent kind of moves around and tries to learn something about the environment. It maps the environment and it figures out where are the objects, where are the free spaces, and so forth. So this is now going a little bit towards, more building agents that can move around, build a map, localize, and also, ideally have semantic understanding of the scene and understand the language and instructions and so forth. And so if we look at these systems are now becoming a little bit more elaborate. So here's one particular system that we've been looking at. The idea here is that you have an image, which is based on the images. You have a mapper block that basically produces the map of the environment based on the image. There is something that's called a global policy that basically produces a target to navigate to. So think of it as some form of, for exploration, could be target of which part of the apartment I want to be exploring. Then there is a path planning module that basically plans the path to reach the goal. And then there is a local policy that basically looks at images, looks at overall path, and tries to produce the action. What is my next action? Go forward, turn left, and so forth. And so many of these blocks are now differentiable, so we can try to learn different pieces of this architecture, as opposed to building, just the reinforcement learning system that goes from these images directly to actions, right? And so here's kind of an example of a system that moves around, training the simulation, but now being transferred to the real world. This is actually bedroom of my student. The little robot that moves around and kind of looks and tries to build the map, the visual map of the environment. So this is just based on the visual, and this is directly transferring it from these virtual environments or simulated environments to the real environments. And this is what, a little robot sort of looks like, right? And so this is exciting because now we can build basically realistic robots that move around, that can build the map, understand the semantic scene. And, ultimately, where are we going with this? As I mentioned before, we want to be able to build agents that can navigate autonomously, that can localize, that can plan, ideally with a memory so you can remember something about the past, deal with multimodal input. We also want to be able to build agents that can reason and understand natural language. So that the idea that, right now we've been looking mostly on simple instructions, given a sentence, try to, understand what is being asked and try to navigate to a particular target. But we want to go beyond that. We want to understand semantically what is it that we're seeing in the scene, and so that we can, understand the instructions and in general understand the natural language as well as perceive human speech. So that's kind of the overall objectives, and we've been sort of working towards many different aspects of it, from language understanding to building robotic agents to incorporating memory so that we can efficiently remember, move around, localize, and navigate autonomously. Okay, on that note, thank you very much for listening to me, and I think that if there are questions, I can probably take some questions.